Okay, well, now we're going to talk about rational functions, do a little bit of review of those. So keep in mind that a rational function is a ratio of two polynomials. And what that means is that you basically have one polynomial, we could call it p of x, over another polynomial, which we might call q of x. So you have basically a division of polynomials. And in this situation, you're going to have a domain that will be all possible x values except for when the denominator is 0, because you can't divide by 0. So the domain of f will be all x values where q of x does not equal 0, since we are writing the polynomial at this point as p of x over q of x. So we're actually going to investigate that a little bit further to talk about what happens to the graph of f of x at those values, the places where the denominator is equal to 0. And so many times we're used to saying, oh, that's where there's a vertical asymptote, but this is not always the case. So we have to make sure we look at both possibilities. So the first possibility is when the numerator is not 0. In other words, p of x, because that is our numerator, p of x is our numerator, would not be equal to 0 at this x value. So in that situation, then you are looking at what you're used to seeing, which is a vertical asymptote. So this would be, I'm just going to write it this way, where p of x does not equal 0. So trying to be as clear as possible, the numerator does not equal 0, but the denominator does, because that's what we assumed when we first started talking about this. I'm just going to write denom for denominator. That would be a little shorter. So I sometimes write this as, I know you call this a hashtag, but I'm old enough to call it a pound symbol, but it stands for number, right? So there's a number. If you were to plug this value in, you would get some kind of number, not 0, over 0. And this is the situation where the function has a vertical asymptote. A vertical asymptote. Asymptote is kind of a weird word, don't you think? At this value, at this x value. Okay. So this ratio of a non-zero number over a 0 is what leads you to a vertical asymptote. Okay, so here's an example. We have this function g of x equals 3x squared minus 12 over x squared minus 1. And we could look at the places where both the numerator and the denominator equals 0 pretty quickly. If we were to just simplify this, I'm going to factor out that 3. And then factor both the numerator and the denominator. They're both difference of squares. So I have an x plus 2, x minus 2 on the top, and an x minus 1 and x plus 1 on the bottom. So this is just a way of writing this function in a factored form. And we can see that nothing simplifies. There's no canceling that can happen. And so there are two values that make the denominator equal to 0, 1 and negative 1. And neither one of those values makes the numerator 0. If I were to plug in 1 or negative 1 up to the top, I would not get 0. So our conclusion would then be that g of x has vertical asymptotes at x equals 1 and x equals negative 1. And in both of those cases, to just be very clear, the denominator equals 0, but the numerator does not at both of those x values. That is what gives you the asymptote. And what does happen, by the way, when the numerator equals 0? What happens when x is 2 or negative 2? Think about that for a second. It would basically make all of g of x equal to 0, right? And what does that look like on a graph? They're x-intercepts, right? If the y is 0. So g of x has x-intercepts at x equals 2 and x equals negative 2, because both of those would have the denominator, the numerator 0 and the denominator not 0. So just a little reminder about that. So let's look at the second situation. So we're still talking about places where the denominator, q of x, is equal to 0. And now what happens if the numerator is also 0? So they're both 0. You were to plug in, you get p of x equals 0, which means that you are looking at both numerator and denominator. Equal to 0. So if we were writing it how I did above, this would be like a 0 over 0 type of scenario. This is not an asymptote. This is a hole. Okay. So the graph of g of x has a hole at this x value. Admittedly, you don't see this very often in pre-calculus, and that's because they usually give us functions in pre-calculus that are already simplified, but there's no rule that they have to be. And so if you have a function that's not simplified and there is a factor that cancels on the top and the bottom, that means your numerator and your denominator are both going to be 0 at that root. So here's an example. H of x is x squared minus 1. We're going to do the same thing. We're just going to go ahead and factor the top and factor the bottom, simply for the sake of looking at what values make the numerator, the numerator 0, and what values make the denominator 0. And you can see the denominator will be 0 at x equals 1. But if I plug that into the top, I also get 0. So our conclusion here is that h of x has a hole at x equals 1. And I want to go just a step further here. You can see this note that I said, be careful when simplifying, because you might have been tempted to say, oh, look, these are the same. I'm just going to cancel them out like this and say this is equal to x plus 1. But you have a small problem here, which is that this function you can plug anything into. So its domain is all reals. But this function you cannot plug anything into. You cannot plug in x equals 1. So its domain is everything except 1. So what you have to do if you are simplifying a function and you cancel out the common term, you have to add that little caveat that x does not equal whatever that root is that you just canceled out, the number that makes that factor equal to 0. So this is a true statement. H of x, this function here, is equal to this function here. But if you didn't have the x does not equal 1, you would not be telling the truth. It would be two different functions. So essentially, this h of x function looks just like the line x plus 1, only there is going to be a hole here at x equals 1. In fact, I could plug that in, x to the x plus 1, I would get 2. So there is a hole at this point, 1, 2, for our h of x function. So it does seem like a technical difference, but it is really important that you realize just because the denominator is 0 does not mean you have an asymptote. You have to check to make sure that the numerator is not also 0. If the numerator is 0, you're going to have a whole. But you need to be careful when you simplify to make sure that you note which x value is getting eliminated from the graph and from the function. Okay, that's the bulk of what we need to talk about with rational functions right now. So let's just do a real quick review of radical functions. Nothing major here. We're going to spend more time with these as we go on in the course. I just wanted to remind you about exponent notation for radicals. So if you're talking about an nth root of x, that's the same as writing it as x to the 1 over n, right? And in fact, if you had a power on your x, like x to the m, that's x to the m over n. So this is going to be an important exponent fact that you'll need to remember. And if we're talking about roots, even root, square root, fourth root, sixth root, right? You can't take even roots of negative numbers. So the domain there would be 0 to infinity. And because of that, you're not going to get out any negative numbers. So your range would also be 0 to infinity. And if I were to graph just the general shape of what one of those might look like, it's going to have that sort of square root type shape to it. I'm just going to write y equals the square root of x on this one. A fourth root and a sixth root have a similar shape. They're a little flatter here by the origin. They kind of go up more like this at first, but the shape is about the same. How that's different for odd roots, you can take the odd root of a negative number. So their domain is all reals, as what is the range. And once again, if you remember, think of a cube root. Do you remember what the graph of a cube root looks like? It's pretty similar, in fact, on this side over here. It's just that it mirrors it on this side over here. So this would be like a cube root of x, and similar in shape would be a fifth root or a seventh root. Again, it's just flatter in the middle. Okay, so just kind of bringing those back up to your attention. And one last thing we're going to talk about in this video are the piecewise functions, everybody's favorite. Piecewise functions really are just functions that are in pieces. So you have a different equation. This particular example has 3 different equations, 1, 2, 3. But each equation only applies to a certain part of the domain. And it's always spelled out in your function definition. So this function is equal to x squared, but only when x is greater than 2. So basically, I would come over here to where x is 2, and I would start drawing, I'm sorry, not greater than 2, that says less than 2. Well, okay, everything to the left of that then. I'm going to draw this y equals x squared graph, which we know is a parabola. It's centered at 0, 0, goes up 1 and negative 1 squared are 1, negative 2 squared would be up here at 4, 2 squared would be up here at 4. Now I'm going to put an open circle there, and that is because you'll see that it doesn't have an or equal to, right? So that graph, the y equals x squared, is for all these values of x less than 2, up to 2, but not including 2. Okay? So I'm going to have an open dot there because I don't include that 0.24. And in fact, if I look at my next equation, it tells me that when x is 2, my y value is 6. So I'm going to go to that same x value of 2, go up to 6, and that is where the filled in dot is going to be. And that is directly told to me by the equation. And then last but not least on this particular equation, I have, okay, bigger than 2, but less than or equal to 6. So between 2 and, let's see, 3, 4, 5, 6, those x values, I'm going to graph this equation, 10 minus x. Well, that's a line. So probably the easiest way for me to do that is plug in its two endpoints. If x were to be 2, 10 minus 2 would be 8. So again, I'm going to go up to that 8 and put an open circle because it does not include this point because it doesn't have the or equal to. But then I'm going to go, what happens at x equals 6? I would have 10 minus 6, which is 4. 2, 3, 4. And that one is going to get a filled in circle because it has the or equal to. In fact, that point is included in the function. And so I'm just going to connect those with a line because I can look and see that 10 minus x is linear. So it's going to be graphed as a line. So that is one way to just kind of approach graphing it, doing it one piece at a time, being careful about your endpoints. Are they filled in circles or closed circles? And I will write out in words how this function evaluates inputs. Okay, so for x less than 2, y is going to be x squared. That's how I would figure that out. For x equal to 2, y is just 6. And for the x's that are sandwiched in between, a stray thing there, y is going to be 10 minus x. So I just plug into each specific equation based on what x value I have. Okay. And what about overall domain and range? What x values are being used for this particular function? Well, when I look at domain, I can see that it goes on forever in the negative direction, right? X is less than 2. That's not limited. There's no lower bound there. But I do have a largest x value. It stops at x equals 6. So I'm looking at negative infinity to 6, and 6 is included. But what about range? If I look at my graph, it's probably the easiest way to tell. I see I have a lowest y value at 0. Nothing's going below that. And it goes on forever. Again, this parabola is just going to keep going. And so I have no upper limit on my y values. So it looks like I'm going from 0, whoops, to infinity. That wasn't much of a parenthesis there, was it? Okay. And you could think of that as x is less than or equal to 6 or y is greater than or equal to 0. Those work too, to kind of talk about what the domain and range are. All right, so there we have a little bit of review of a couple different types of functions we're going to be working with this semester.